All right, welcome to lesson 23, Piece of S in Energy Maneuverability. This is the fighter pilot's lesson. This is what we've been building to all along. This is where we will answer the question, how do I beat another airplane given my advantages? And we also get to finally answer the optimum trajectory question for the Streak Eagle problem. Now, if you recall, in 1975, we wanted to take back the record from the Russians. The MiG-25 had taken the time to climb record. So the 30K, 100,000 feet time to climb record. February 1975, we take an early production F-15A up to Grand Forks, cold North Dakota. And we set 8 time to climb records. And so now we get to answer what is the optimum trajectory and how do we do that. So if you have this problem, after today you will be able to answer the question, where do we fly, how do we fly, and how do we take back the record? So let's review energy and power. So this was, we discussed earlier during the power lesson that this is a rate question. We're trying to get to altitude in a certain minimum rate of time. So that's a rate problem, rate of climb problem. So it's a power problem. And power is the time rate of change of energy. And of course, energy and work are equivalent. And we remember work, a differential work is a force times a distance. So a rate of change in time of work is, take the derivative of f dt or f dx, force times the distance. The force doesn't change over our time, so dx dt, which is force times velocity. And of course, in our free body diagram of our airplane, we're talking in the x direction here, so we've got the force of thrust, drag, and of course lift and weight to be complete. So this force right here we're talking about is the net force, the thrust minus the drag. So power is equal to velocity times my net force, which is my thrust minus my drag. Now recall this drag component had 2 parts. It had the parasitic drag as well as the induced drag. The induced drag is going to become very important later on when we talk energy maneuverability, which is pulling G's. Pulling G's is going to increase our lift coefficient. That's going to increase the induced drag and is going to result in more drag and less power, excess power available. So we had parasite and we had induced as part of that drag term. Now it is very convenient and very useful to make a distinction between the types of energy states. So if we had an F-16, a 30,000 pound F-16 and a 60,000 pound F-22, both at Mach 0.9 at 35,000 feet, the heavier F-22 is going to have more energy. And 747 at Mach 0.9 at 35,000 feet is going to have more energy than the F-22. So let's take the mass, or the weight rather, out of the energy equation. So let's, energy, there are 2 types of energy. Total energy is going to be the sum of kinetic energy and potential energy. And kinetic energy is going to be 1/2 mv squared, and potential energy is going to be mass times gravity times how high it is. So in order to neutralize the amount of energy here, let's divide through by weight. So energy per weight is going to be, let's see, let's bring this over here. So it's just going to be H plus we're going to have a 1 over 2g v squared. And this is going to be, it's really easy to see right here, it's going to be in units of height or units of feet. So we're actually going to call this energy height. And P, power, is the rate of change of energy height. And in this case, we've taken the weight-specific energy height. So if we take the energy height with respect to specific to weight, we're going to call that P sub S. So P sub S, what the whole lecture is about, is the time rate of change of energy height. So we have the rate of change of height there, and then this is a very simple derivative to take. We have 1 over, so we're going to have V over G dV dt. This is P sub S, the time rate of change of energy height, and there's two components to it. Rate of climb, and there's going to be essentially an acceleration term, a dV dt times a velocity. This will have units. If energy height has units of feet, P sub S is going to have units of feet per second. So let's go back and look at our power equation here, where velocity was times our net force. And if we divide this P by W, we get, again, P sub S. And we're going to have another expression now. Let's write this down here. Well, another expression for P sub S. So there's three conditions that we should look at here. First, let's consider when P sub S equals 0. Assuming the non-trivial case where V is not equal to 0, or we're actually flying the airplane, the only way for P sub S to equal to 0 is for our thrust to equal our drag. When our thrust equals our drag, we are not going to accelerate, nor are we going to have any excess thrust in order to climb. So our P sub S equals 0, which means that we are not going to be climbing and we're not going to be accelerating. That makes sense. When P sub S is greater than 0, that means our thrust is greater than our drag. And with that positive P sub S, I can either climb, or I can accelerate, or I can do a combination of both. I am gaining energy when my P sub S is greater than 0. When P sub S is less than 0, I have more drag than thrust. So either my thrust is insufficient for the drag that I have. And when could that happen? That could happen if I'm pulling G's. So I'm pulling G's, I've increased my induced drag, increased my drag term, exceeded my thrust, and now my P sub S is negative. When my P sub S is negative, one of two things, or a combination of those two things, has to happen. I either need to descend, or I'm going to be slowing down. And in the case of dogfighting, often we do both. Often dogfighting is a descending fight, descending in altitude, and if we start at a high speed, we're also slowing down, which, if you recall from our previous lesson, will, up to a point, decrease our turn radius, which is desirable, and increase our turn rate, which is also desirable. So in general, when we're dogfighting, we would like to have positive P sub S, have more P sub S than the other airplane, but we also want to balance that with where we are in the flight envelope and how we're going to manage that. As we're pulling G's, so for example, in my F-16, when I'm pulling 9 G's, this drag term is going to be very, very high, and I am generally going to be in a negative P sub S state. So we can plot, this is an energy height plot. So let's write down the equation again for P sub S. And it was also dH dt plus V over G dV dt. So these are contours of equal energy height. We don't really need to label them because they're labeled right here. When our velocity is 0, our energy height is given. So here's the 10,000 foot energy height contour. So when I am on the deck at a little bit more than 0.7 Mach, that is equivalent to being at 10,000 feet of altitude with 0 energy. So here's all kinetic energy, here's all potential energy, and I can trade that energy anywhere along the line. Similarly, the streak eagle, trying to get up to 100,000 feet, as we study the trajectory and look at the optimum way to start from here and get to somewhere here for the streak eagle, there is some trajectory through space here that is going to give us the optimum climb. And that is the streak. Everything you need to know about energy height is actually encapsulated in the Air Force song. So let's say that we're flying high cap. We're up here in an F-22 in the high 40s, orbiting at 0.8 Mach. And there's some bad guys down below at 20,000 feet coming screaming in at a high Mach number. They can zoom along this energy height line. They can zoom to meet our thunder. And of course, down we dive. We can dive down along the energy height lines. So that is what the Air Force song is all about. It's all about energy height. The things that they never told you. So here, let's take a closer look at the streak eagle problem. So again, here is our formula for P sub S. The streak eagle is going to be starting here at 0 knots in February, Grand Forks, North Dakota. And we want in the minimum amount of time to get up here to 100,000 feet. We don't care how fast we're going, but we want to get to the altitude. So it turns out that if we look at P sub S, and we'll talk about how we do this later on in the lecture, this is from Jet 10. You've got all the tools you need to recreate this. So these are the different P sub S energy heights. So what the F-15 did is it started, and here's actually the flight test data, it took off, remember it took off in about 4 ship lengths. It accelerated along the runway, and then it started to climb. And it actually went supersonic. It did that Immelman going up, and then came up in about 30, completed the Immelman maneuver. And what you see is it's actually going up through points here of contact where the energy heights are hitting these contours, these P sub S contours at maximum points. And then it completed a level accel. So 200 feet per second, this little dip down here is the supersonic drag rise. And here's the 80,000 foot energy contour. Here's the 90. So here's the 100. So somewhere along here, we want to intercept this. And to the extent that we're positive P sub S, and everywhere inside here is positive P sub S, we'll actually be gaining energy height lines. So it might be about right here at, let's say, at the 90,000, and we start now our climb. We're already going Mach 2, 60-degree climb, and we're constantly, because we're still positive P sub S, we are still gaining energy height until that point. That is the optimum streak eagle trajectory. And here's the actual flight test data from a NASA report. So here is a generic P sub S equals 0 envelope. So right here, remember there's a CL max that you can't go greater than. And some places you can't go any faster because you'll exceed the structural dynamic pressure of the aircraft, so you can't go any faster than this. Right here this is P sub s equals 0, and this is the dynamic pressure limit, so in level flight, that's the fastest you'd be able to go. Now, some aircraft also have a Mach limit. In the case of the F-16, it's for the engine, among other things. So 2.05 for the Mach limit for the F-16. So here's again P sub s. So anywhere inside of this P sub s diagram, so long as you don't exceed a boundary, you can get your airplane. So you can fly anywhere in here. You can reach point 2. Now outside of the P sub s line, you're a negative P sub s. That doesn't mean that you can't get there. It simply means that you can't stay there. So for example, if you were at point 1, you could zoom up to point 5, up to 0 velocity. Now you wouldn't stay there. You would, if you got to 0 velocity, let's say you're an airplane flying straight up, you would reach a point where you would do a tail slide and start coming back down. Point 3 is the maximum speed that you can achieve. It's the highest V or Mach number that you could achieve in level flight. Of course, in this case, that's greater than the Mach limit. So you really don't want to go there. There's a good story I can tell you sometime about a young second lieutenant academy grad that took the F-16, which has a speed limit of 800 cal. So this is a cal limit of 800 knots. He achieved 892 knots and got a great call sign out of that. So remind me sometime, I'll tell you that story. Point 2 is the max sustainable altitude. So here's the highest H that we could achieve and stay there. Of course, we can obviously get higher. We can get to 0.5. Point 4, again, like Gordo did, that lieutenant I was just telling you about. He's lucky he arrived. In theory, you could get there, but again, you've exceeded the Mach limits. Point 7 is an unattainable spot. And so, because the energy height line through point 7 exceeds where your P sub s equals 0. So there is no physical way that you could get to point 7. So here is an example of a climb schedule. This is very similar to what the Eagle did. This is actually the P sub s diagram for an F-104. And you can see once you get going fast, there's these regions out here. If you remember how the power available curve for an afterburner looks, the faster you go, the faster you get faster. And again, since P sub s is equal to your excess thrust, as your Mach number goes up in AB, your thrust is going to increase. So there's regions out here where you might have these islands of very positive P sub s. So for example, again, there's a neck down here at the supersonic drag rise. But if you wanted to get out here, a very easy way to do that is to climb through the peaks here. And in this case, we are climbing through optimum energy points. We'll talk about that in just a second. And then you dive down out here to where you have these regions of positive. So right here, we are between, here's the 100-foot line, here's the 200-foot line. So this might be 150 feet per second. And as you get closer and closer, now we're closer to, here's the 200, now there's the 300. And if you're going to go here, you could achieve 400 feet per second. Which means when you are pulling G's, again, G's are going to increase your induced drag. Out here, you might be able to sustain G's that you can't in this region while you're slower. So let's talk about a subtle nuance. Here are constant contours of specific excess power of P sub s along with energy height curves. there are 2 points of note. So these are where you achieve your maximum rate of climb. But that's not your maximum rate of energy. If you were to look, so this point right here has a slightly greater energy height than this point. So where the energy height contours are tangent to the P sub S contours, that will be your optimum climb path, and that's what we did here. So again, if you're going to set a record like the Streak Eagle, where you're trying to get to a maximum energy state, you're going to want to climb through these points where your energy heights are tangent to your P sub S lines. If, however, you want to maximize your rate of climb, you'll do that through the dH/dt. And again, this is very easy to see. If we write P sub S in terms of dH/dt plus V over G dV dt, and of course this is rate of change of energy height. There's points here at slower speeds where my dH/dt is greater. So at a constant P sub S, if I decrease my V, I can increase my dH/dt up to a point. So at slower speeds, you can achieve a greater rate of climb, but it's not going to be your greatest of overall energy increase. So this trajectory right here that goes through the tangents is called the Rutowski climb schedule, named after Rutowski. This is the report that he wrote, a copy of the report that he wrote back in 1953. And here's a graph straight out of it. So we built an entire generation of aircraft, the Century Series fighters, based on this particular theory of getting fast and going fast. So here is the 1G P sub S for the F-104 Starfighter, Century Series fighter based, again, on the thinking motivated by Rutowski. Now at 3 Gs, look what happens. So as we pull Gs, as we increase Gs, our parasite drag isn't changing. That changes with airspeed. But our induced drag does change with G, because again, induced drag is drag due to lift. G's are produced by producing more lift. Remember, NZ equals lift over weight. And so as we pull G's at 3 G's, we're going to have more drag. That's going to take away some of our positive P sub S regions here. So at 3 G's, this is what I'll mark where the 0 is. So on 3 G's, the 0 is right here about where the 200 is. So the 200 foot per second line is about where the P sub S equals 0 line is. But you still have this area out here. So you could be at 1.8 Mach at 30,000 feet and be in a 3G turn in your F-104 and stay there all day, or at least stay there until you run out of gas. So as I said previously, we built an entire generation of aircraft based on the thinking in terms of how do we get fast and go fast. And it made sense for the era. Through the 1950s with the Century Series fighters, we were worried about the bombers coming over the horizon. So we wanted high altitude interceptors to intercept those bombers before they could deliver nuclear weapons. So we were designing supersonic interceptors that were Mach 2.5, Mach 3 aircraft. Those oak aircraft, though, the ones that go very, very fast and very, very high, don't necessarily work as well in a dogfight. And that's a lesson that we learned during Vietnam. The thinking changed with energy maneuverability. This is John Boyd. This is a copy of John Boyd's report. This was originally classified. It has since been declassified. and he introduced the concept of energy maneuverability. This is my F-16-1-1. It is a thick book. There are thousands of pages in this, and you spend a lot of time as a fighter pilot looking at this. So here you have, these are energy maneuverability diagrams, what we are going to talk about next. And what you'll see lined up here, there's the 0 PSS, there's the 200 foot per second, 400 foot per second, 600 foot per second. This is a F-16 in a certain configuration. So we've got a 15,000 feet. This is in max AB, 22,000 pounds. That's a drag index of 0, so this is there's no stores, no tanks, nothing on here, and this is fairly lightweight. As you go up in altitude, you are going to have less PSS, just like we saw on the other diagrams. So this is all physics. This is the same for any aircraft. You've got turn rate against airspeed, you got lines of constant radius, pure physics, airplane doesn't matter. Once we superimpose PSS curves on here, though, we are now talking about the performance of a specific aircraft. So let's say, in this case, there are different G factors. Oftentimes, the way we actually first do this is via a level acceleration. So in flight test, we will start at a certain airspeed and we'll accelerate without pulling G, so at 1G. So this is the 1G curve. Because at 1G you have no turn rate. And you accelerate out. And you call it airspeed. So for example, every 2 seconds you'd say ready, ready, hack, ready, ready, hack, and you call it the airspeeds. By measuring the time in between that, so again, PSS equals dH dt. Since I'm doing a level acceleration, this is 0. Plus v over g dv dt. The dv dt comes from so I'm calling out constant intervals of time, and my dv's are just what my velocities are, or let's say I'm calling out airspeeds every 2 seconds. And so now I can determine PSS along a term. It might be 800 feet per second here, or 400, 600, 800, 1,000, 1,200, and then start decreasing again as I get to the Mach number until I reach my maximum speed, at which point I stop accelerating. My PSS equals 0. There's another flight test technique called we can either do it via level turns, sustained turns, or wind down turns, where you stabilize at an airspeed and at a certain G, so in this case 2 Gs, determine what my airspeed is in maximum AB. And then you increase the G, the aircraft's naturally going to slow down, and that'll give you the points along here where PSS equals 0. This flight test technique can be quite painful, particularly if you have a 9G airplane or a 7G airplane, and you can sustain 7 Gs because it takes a while for the airspeed to stabilize. So your turnaround and maximum AB at 7 Gs, and hopefully you are well hydrated and you had your Wheaties that morning. So we can draw contours of different PSS's on the diagram, and when we do that, we ultimately end up with a PSS diagram, an energy maneuverability diagram, rather, with PSS contours on it for a specific aircraft. So again, this is my F-16 at 15,000 feet in maximum AB, drag index of 0. The gross weight is 22,000 pounds. And from here, I can see that my maximum sustainable turn rate, so sustainable means I can stay there. So my PSS equals 0 feet per second. So that occurs right here. It is in excess of 7.5 Gs. So there's the 7G line, there's the 8G line, 7.5 Gs I can sustain, and that happens at about 0.9 Mach. Now that is not, however, my quickest instantaneous turn. So my quickest instantaneous turn is up here. It reads it actually off for us right here at 19.1 feet per second. There's 20 degrees per second. I said feet per second, it's degrees per second. So 20 degrees per second. Here's 19.1 degrees per second. And we call this low corner, we call this high corner. The point of this lower point right here, this lower corner, is I've actually got a smaller turn radius. So there's the 3,000 foot turn radius line. Here's the 2,000. So my turn radius is just a little bit more, and my turn rate is just shy of 20 degrees per second. Now at that point, I've got negative P sub s. So in this case, here's minus 600, minus 800, and minus 1,000 feet per second. So P sub s dH dt plus V over G dV dt. So if I am at this point dogfighting in my F-16, I'm turning 20 degrees per second, and I'm at 15,000 feet, but I can't stay at 15,000 feet. So if I'm going to sustain this airspeed, so if I'm going to maintain around 0.75 Mach here, the only way I can do that is to descend in altitude. So two types of problems that we can work. We can just work the problem where we're calculating the turn radius and the turn rate. We did this last time, given conditions. But once we start maneuvering two aircraft in relation to each other, we are trying to decide who has the advantage, who can, and it comes down to P sub s, it comes down to energy maneuverability. Who can sustain the turn for the longest period of time, and who is going to outrate the other person in order to be able to turn first. So ultimately, we want to know, is my airplane going to beat the other airplane? And we can see the regions in red, which are the MiG-21. So here is a P sub s equals 0 line. Here is the stall limit line for the F4. And so there are whole regions here where the MiG-21 has exclusive advantage. So right here, for example, the MiG-21 is at 0 P sub s. It can sustain that. And the F4 is at -5. I'm going to guess that that's probably 500 feet per second. Negative 500 feet per second turn, just shy of 5G. So the F4 is not going to be able to turn with the MiG-21. Now the F4 does have this region out here. They're fairly matched, 0 P sub s out here. It can go faster in here. But this is why the F4s had such a hard time in Vietnam with the MiG-21s. Because where we usually end up turning and fighting is here. When we're going high speed, our turn radius is here. Look at this. This is 1,000, 2,000. It's hard to read that, but that's probably 10,000 foot turn radius. So 2 mile turn radius. Not exactly what you want to do when you're dogfighting. So the tactic the F4s used was actually to check and extend defense. They would actually run away from the fight, get a couple miles away, and then turn around and then try to use its missiles. Of course, during that time period, the missiles that we had, both the radar guided and the infrared guided, were nowhere near as capable as they were today. Another way of presenting it is with color here. So again, this is very, very similar to what we saw. This is still the MiG F4 and the MiG-21 comparison, although we've now got it at 1G and then at 5Gs. And once you start turning, you can see there is this region of exclusive advantage is the deep red, and then the lighter pink is somewhat superior, but both of those grow, except for the very, very high altitude here as we start to pull Gs. Now, where do they get those diagrams from? These diagrams come from the Intel. How do the Intel folks get it? Unfortunately, of course, we can get ours by taking them into flight test. Unfortunately, the Chinese have not let us do a J-20 flight test. So they do exactly what you'll be able to do. Intel folks, we have aeronautical engineers that are working at NASIC that are looking at foreign designs, looking at the geometry, making assumptions, and deriving what they think the performance is. and then publishing it in diagrams just like this or in diagrams like this so that we can make the comparisons, and before we get in the fight, decide where we want to fight. All right, so that's lesson 23. Lesson 22 and 23 are very closely coupled with each other. I encourage you to pause and review the DLOs from each of these lessons. Again, ultimately what we care about is, where are we better? Know yourself and know your enemy, and in 1,000 battles you will know victory.